Welcome again. Thank you for joining us today. Our speaker today is Alex Damour from Google Brain. We're really excited. So I'm just going to quickly introduce the Trustworthy ML Initiative. We are a group of people who are interested in this broad area of research, causal inference, interpretability, fairness, robustness. Our initiative has multiple different goals. We have a bunch of different programs to help us achieve that. We have a list of resources on our website. We have an active Twitter account. We have a platform to showcase work from early career researchers. Excitingly, we are also now starting to get organized and plan for our symposium that is going to happen in September or October, so after summer. So if any of you are interested in helping to organize that, please get in touch with us through our email. Okay, now back to today's agenda. Today's session is divided into two parts. The first hour is a talk and a moderated chat with our speaker, Alex. And the second hour is a free-flow participant discussion. So Alex is going to give his talk until 12:45 p.m. Eastern Time. If you have any questions at all, please submit them using the Zoom Q&A tool. So Zoom Q&A tool, not chat. That would help us keep track of your questions better. At 12:45, we'll do the Q&A and the chat with Alex about his journey in machine learning. And at 1 p.m., we're going to take a 5-minute break and reconvene at 1:05 Eastern Time for participant-driven discussion. Okay, without further ado, we are very honored to have with us today our speaker, Alex Damour from Google Brain. Alex's work primarily focuses on the interface between machine learning and causality. He has worked on applications in a lot of applications, network analysis, sports, healthcare, education, marketing, finance. Before this, he was at Berkeley and he got his PhD from Harvard. Okay, without further ado, Alex, take it away.
Fantastic. All right, let's see here. Make sure. All right, can everyone see my screen now?
Yep, we can.
Fantastic. All right, I'd love to thank the organizers so much for having me today to talk about some of this work. This is work that I managed to do in collaboration with a large number of people, both at Google and outside of Google. But I want to acknowledge my sort of co-first authors, Catherine Heller and Dan Moldovan, who worked with me over the course of the last year on a sort of larger initiative inside of Google to try to understand credibility issues that can come up in machine learning systems when we try to deploy them in the real world. So in this talk specifically, I'm going to talk about a paper that shares the title of the talk, Underspecification Presents Challenges for Credibility in Modern Machine Learning. This paper is up on arXiv now, and I believe was sent out with the talk announcement. So let's move on. All right, so I think an issue that is near and dear to the hearts of many people involved in the Trustworthy ML initiative, right, is this notion that machine learning in the lab is not the same as machine learning out in the world, right? In particular, if we see that a machine learning method is successful in the lab, that doesn't always mean that we can just take that model and immediately ship it out into the world and expect that it's going to have beneficial effects out there, right? And so, to understand sort of a number of different ways that this gap between machine learning in the lab and machine learning in the world can sort of arise, I was recently reminded of this quotation from Donald Knuth by Sarah Hooker, who's one of the this initiative's organizers, right? That this is actually from the preface of this book. So I've read exactly one page of this book, but it is a classic. So these machines have no common sense. They do exactly as they're told, no more and no less. I think this quotation really applies very nicely to how machine learning tends to work. And in particular, I really like this no more and no less comment, because I think it gives us sort of a nice way to understand different ways that machine learning can fail. So let's talk about some potential failure modes, right? So one potential failure mode is when the machine does no less than what we've trained it to do. And so this is a failure mode that we discuss a little bit in the paper that we call structural conflict. And this is a case where there is an actual structural difference between the problem that you have asked the model to solve and the problem that you really mean to solve out in the world. Right, and so this essentially constitutes training a machine to solve the wrong problem, right? So it's doing no less than you asked it to do, but that thing is not the right thing, right? And so this kind of structural conflict can arise in a number of different situations. For example, if you are measuring and thus optimizing the wrong thing, if there's a sampling bias in the data that you're using to train your model, if there's some form of leakage. So a nice example of this kind of structural conflict issue. And then if we wanted to sort of analogize this to different failure modes that we see in, say, software engineering, right? We tend to think about structural conflict issues as being like bugs, right? They are discrete failures that came through the design process. So an example of a predictor doing no less. This does arise a fair amount in medical applications of machine learning. This is an example from that was presented in JAMA Dermatology of a convolutional neural network that was trained to classify skin lesions as being benign or malignant. And one interesting thing that arose while testing this model is that the training data actually included, in some cases, markings with surgical ink around lesions that were determined to be malignant. Right. And so what this means is that when the model was being trained, right, and the model was meant to be a sort of diagnostic tool that a doctor could use to aid in making a diagnosis before a decision had actually been made, this diagnostic model was actually being trained in part on post-diagnostic data. Right. So what this means is that when there was surgical ink that appeared in an image that was sort of leaking some information to the algorithm that this is actually a malignant, this is actually a malignant lesion. And so in testing this model, what these folks did is they would take an image of a lesion, they would ask the model the probability that it was malignant, and then the researchers would actually go in with surgical ink, mark that exact lesion, take another image of it, now marked with surgical ink. What they found is that when you move from the left image to the right image, the model's output probability of predicted malignancy goes up, right? And it goes up substantially in every one of these images that they looked at. So this is an example where a model was trained to make use of some leakage, right, that was not going to be available at the time that it's actually deployed. And so I think that these kinds of issues where you have trained a machine learning model on a problem that is fundamentally misaligned with your application area. This issue has had a number of very high-profile examples in the literature. And it's an extremely important one. But in this particular paper, we wanted to focus on a separate failure mode that sort of corresponds to a model doing no more than you've asked it to do. And so we call this particular failure mode underspecification. That's where we're going to focus on here. Right. So when when you have an underspecified problem, the way that we think about it is that you've trained the model to solve a fragment of the right problem. Right. So the fragment that you've asked the model to solve is very well aligned with your goals. Right. So if you trained a model to predict on this problem very well, then that is that's something that may be necessary for your model to be successful out in the world. However, we've only asked the model to optimize that one thing when in fact we have many other requirements of what the model ought to do, right? So for example, we may have additional criteria that fall under this trustworthiness umbrella, including robustness, fairness, causal grounding, et cetera. And so, right, to make this analogy to software engineering, if structural conflict corresponds to having code that has bugs in it, we think about underspecification as sort of corresponding to untested code. Right. And the sort of thesis of this talk and of the paper, right, is that if we follow standard practice, deploying machine learning can resemble shipping untested code. Right. And so we're going to focus on this specific failure mode and focus specifically on how even when you have a problem, or even when you have specified a learning problem that's very well aligned with your application, you can still end up with unexpected behavior when you deploy a model out in the world. All right. So I'm going to go into a little bit more detail about what exactly we mean by underspecification. Then I'll pause for questions after I provide this set of definitions. Right. So to understand underspecification, let's all sort of go back to machine learning 101. Right. So right, when we think about a machine learning pipeline, we think that there's some data that we've drawn from the world. This particular view on the world we'll call the training domain, right? That actually produces some data for us that we're going to use for training and validation of our particular model, right? And then in sort of a standard machine learning pipeline, right, what you might do is then take an independent draw of data from the training domain, or, you know, as it usually happens, we'll just sort of apply a completely random train test split, right? And then we will test our model on this independent sample of data. But the key thing is that the training / validation data and the test data all come from the same distribution. They all come from the same view of the world, right? And so we'll call these kinds of evaluations IID evaluations. And so while I'm going to be talking about how IID evaluations are not sufficient in this talk, I think it's important to also acknowledge that these kinds of evaluations have been sort of machine learning secret sauce, right? They are, right, one might argue, sort of the reason that machine learning has taken over a lot of quantitative analysis out in the world, right? Because it's a very well-defined way to ensure that a model that you have trained actually encodes some kind of stable structure about the world, right? It's stable enough such that it can survive even after you sample completely independent data from the same distribution. So, you know, getting a model to pass these IID evaluations is not trivial, but at the same time, right, as I'll be talking about as we go on, right there, it's not sufficient to ensure that the model is going to be successful out in the world. All right, so when we talk about underspecification, right, we say that an ML pipeline is underspecified if it can return multiple distinct predictors that achieve equivalently strong IID generalization performance. So what do I mean by that? I mean that when we specify a machine learning pipeline, there are usually a set of things that we have intentionally designed, right? Something like a model architecture, the training data that we're going to use, right? And but even when we specify those aspects of the learning problem, there are a bunch of other choices that we have to make to actually train the model, right? And based on those choices that we make, and they can be anything from the type of optimizer that we're going to use all the way down to the random seed that we use to initialize the model, right? It's possible that the same machine learning pipeline with the same design decisions baked into it is going to return a bunch of, could return a bunch of different kinds of predictors, right? And now each of these predictors, right, this is sort of the, the actual mapping from inputs to predictions that you might, you know, sort of ship out into the world and do inference with, right? Each of these predictors may look identical according to your standard IID evaluations, but these predictors may actually have very different performance on trustworthiness or credibility criteria, right? So, for example, they may exhibit very different fairness characteristics, or they may encode very different stories that you could interpret as sort of a causal story about how the inputs are related to the predictions. All right, so just to give a sense of what underspecification can feel like, right? I'll just show this this video.
This is a square. Can you guess which spot that goes in?
The square.
That's right. It goes in the square hole.
Yes. Okay.
And how about this rectangle? That one
Also the square.
that goes in there too.
Yeah.
Up next, we've got this thin rectangle.
The thin
Can you guess
rectangle.
where that
The
goes?
thin rectangle.
That's right. It goes in the square hole. And up next, a cylinder.
The circle.
I think that goes in
The circle.
the square hole. Now, we've also got this semicircle right here. Do you see a slot that would fit
The semicircle.
semicircle?
The semicircle.
That's right. It's the square hole. Okay. Up next, the triangle. We know what hole that goes
The
into,
triangle.
right?
Triangle.
That's right. The square hole. And up next, we have the arch.
The arch. The
You
arch.
guessed it.
The arch.
It goes in the square hole.
All right. So, oops, let's see. Yeah. So I think a number of us who have worked with machine learning models and tried to probe exactly what the decision surface looks like may have had very sort of similar experiences to, to finding that, if our IID test was just to see whether or not all the blocks made it into the bucket, right, we would actually be quite happy with that solution. But then when we actually try to probe the solution a little bit more to see whether it satisfies some of the additional trustworthiness criteria that we have, we find that the model has actually solved the problem in a completely different way from how we would have wanted to originally, right? And so this is sort of the essence of underspecification, that the success metric that we specified, in this case, IID generalization, is just not sufficient to ensure that the model actually satisfies all the criteria that we had in mind, right? And that would ensure that the model is actually successfully deployable out in the world. So the key observations that come from this work here, right, are that underspecification is ubiquitous in applied machine learning, right? And that predictors can behave very unexpectedly in practice, even when the prediction problem is very well aligned with our application, right? Even if getting all the blocks in the bucket really is very important in practice, right? It's we can still see that the model behaves in a very unexpected way, according to what we had in mind as the proper way for the model to solve the problem. In particular, when underspecification is present in a problem, it can mean that, right, the sort of trustworthiness behavior that we have in mind for a particular model is so poorly specified or so poorly constrained that even very small choices that we make for convenience and actually in actually training the model can affect the real world behavior of the model and have real consequences once we take the model out into the world. And so after sort of specifying all these problems, right, what it really highlights is that there's a lot more work to do in the machine learning world in terms of specifying, testing, and enforcing the behavior that we require of our models for them to be trustworthy. Great. Okay, so are there any questions about this sort of notion of underspecification?
We don't have any questions so far, so
awesome.
Maybe yeah, want to encourage the audience, if you have any questions, please post them. Yep.
Awesome. Great. Yeah, so let's talk about detecting underspecification in neural networks, right? So right, this is sort of getting into the heart of the paper. I emphasized earlier that this involved a lot of people. And it involved a lot of people because we wanted to look at machine learning models that have been applied in a lot of different application areas. And to make sure that the models that we were using were ones that were actually sort of like not toy, but large and production ready enough such that one could plausibly think about putting these into some product that operates out in the world. Now, a lot of the models that we ended up using were sort of precursors to that sort of thing. But what that meant is that, right, every one of these examples that we worked on involved a team of people who was sort of working on this model as its own sort of research product, right? Great. And so for each one of these models that we were looking at, what we wanted to do was to apply a single experimental template to show that even if we took the sort of full specification of a machine learning pipeline, along with the evaluation criterion that we are going to use, right, the sort of trustworthiness properties of the predictors that this pipeline was going to return would be sensitive to very small changes that we apply, right? So that would mean that the trustworthiness of these models was not very well constrained by the entire pipeline that we were using. And so in order to do that, what we needed to do was first to construct a metric for measuring exactly what the trustworthiness criterion was that we were thinking about. And so we called these metrics stress tests, right? So the idea here was that we wanted to have these concrete tests that encode the specific requirement that we have of the model. So that could be something like we want to measure the model's performance, be that accuracy or AUC or something like that, under a distribution shift. Or maybe we're interested in how sensitive the particular predictions are to a change in some of the inputs that are passed into the model. Right, so you can imagine a number of different stress tests that that can be used to sort of witness whether a model is actually reasoning through the problem in the way that we want to, and is operating in a way that can sort of engender trust. The next thing that we do after we choose a stress test for a particular model is we construct an ensemble of models. So when we say an ensemble of models, what we mean is that we want to find a set of predictors that come from the pipeline, where we think about the sort of core design of the pipeline as remaining fixed. But any of these other degrees of freedom that we might choose for convenience to potentially vary. Right. And so there are a number of different sort of arbitrary choices that we can think about with a fixed that we can think about with a fixed machine learning pipeline. So these could include things like the random seed that you use to initialize your model. They could include hardware, the optimization algorithm, opaque model choices where you really like the way that we think about this is really anything that you would be willing to sort of throw into a sort of AutoML type black box optimization, where you don't have a strong preference in terms of the design of the problem. These are different arbitrary choices that we'd like to assess sensitivity to. And in particular, the one that we really focused on was random seed, because regardless of your perspective, I don't think anybody would argue that the random seed is an actual design parameter for their particular machine learning algorithm. All right, so once we construct a set of models that differ only by these arbitrary choices, we then confirm that among this set of models that we've gotten from the same machine learning pipeline, their IID performance is equivalent, right? So we do the same IID evaluation for all of them, right? And what we want to do here is make sure that the arbitrary choice that we're varying is truly arbitrary, right? That it's not something that in practice we would have a strong preference just following the standard machine learning pipeline to choose one of these choices over the other. All right, and then the final thing that we do is measure variation in stress test performance across all of these different models that we've generated from the same pipeline. Right, and in particular, right, if we see that there's large variation in stress test performance, right, that means that the model's sort of trustworthiness behavior is sensitive to this arbitrary choice in the ensemble. Right, and so if we see large variation in stress test performance, this indicates that that the machine learning pipeline is underspecified, right? That there are some criteria that we have in mind that are in fact not constrained by the machine learning pipeline as we've implemented it. Okay, so let's see, I could pause here for questions, or I could talk through a couple of examples.
We have one question, which might be perfect for this time actually. So the question is from Preeti, asking what is the difference between underspecified and misspecified? Yeah,
I think that's a great question. So the way that we've sort of characterized this, I would say that misspecified may actually fall under the solving the wrong problem or structural conflict sort of scenario, in the sense that right, if we think about the misspecified model as solving an like approximate version of the problem, on which we've sort of projected the real problem onto this, approximate version of the problem, there is a real possibility that right, that solving that approximate problem is not necessarily going to solve your main problem. So there's certainly one aspect of misspecification that falls into that category. On the other hand, I could also see that right, it's possible for your learning problem to be underspecified if, for example, there is a set of misspecified models that you would be willing to choose from in a particular problem. And within each sort of misspecified class, there is a best model, right? And the best model within each of those misspecified classes sort of performs very similarly on your IID evaluations. So yeah, I guess like misspecification can show up in either like in either aspect here. One thing that I want to emphasize is that we're thinking about underspecification as a property of the entire learning pipeline, right? So not necessarily just a function of the architecture that you're choosing or the loss function that you're choosing, but really the entire decision process that goes from having a problem that you want to solve all the way to like evaluating whatever decision function you end up with, and deciding that it's ready to deploy. And so like the aspect of that pipeline that we really focus on in this paper is sort of filtering those decision functions based on their IID evaluation performance. Right, so there are many different ways that misspecification can sort of map to different IID evaluation performance. Yeah, so that's a really great question. Thanks for bringing that up. Great. Cool. So let's talk a little bit about how how detecting underspecification might look in a number of different computer vision applications. So there are 3 different computer vision applications that we looked at in this paper. One of them is sort of on your in the lab computer vision problem, where we train a set of models on ImageNet, and then we look at how those models perform on the standard ImageNet validation set versus how they perform on corrupted versions of ImageNet, or the ImageNet C benchmark, which has become a very important part of robustness research. It's from Dan Hendricks and company, Thomas Dietrich as well. Right, and then in addition to this sort of like in the lab evaluation of robustness, we also looked at 2 different cases of how models behave under sort of natural distribution shifts. So one of them was an application in ophthalmology using a model that's designed to do diagnosis that's based on retinal imaging. And then another one was based on dermatology for a model that was designed to suggest different skin conditions based on an image that somebody has taken of their own skin. All right, so our experimental protocol here looks like, right, remember we have in mind a particular stress test that we'd like to apply. So in this case, in this ImageNet example, right, we are looking at how a model that's trained on clean ImageNet data might generalize, or what its accuracy might look like if you were to apply it to a data set where different corruptions have been applied to standard test set images. So for example, here we have a picture of a bird, right? And then if we apply the pixelate corruption, then this is a pixelated image of a bird, right? We'd like to understand whether a model trained on clean ImageNet can actually predict well when these corruptions have been applied to the test images. And right, this stress test is in fact a sort of a large collection of stress tests that include different kinds of corruptions. There are many more than I have listed here on this slide. But they include, corruptions to brightness, applying Gaussian noise, pixelating, or applying JPEG compression. Okay, so we've chosen our stress test. Now what we'd like to do is construct an ensemble of models, right? And so here what we did was we looked at the standard ResNet 50 architecture for doing image classification, and we looked at initializing it from 50 different random initializations taken from the same initialization scheme, right? And so everything else that we did to train these models was exactly the same, right? We use the same hyperparameters, we use the same stopping criteria, right? Everything, every one of the choices that you have to make in practice was the same, right? Same optimizer, right? And upon doing that, right, what we find is that when we estimate the accuracy of all the models in this ensemble, right, their accuracy is very tightly clustered together, right? In fact, the y-axis here is standard deviations of the accuracy that we see in this standard test set here, right? So like on IID evaluations, all these models perform very similarly, right? So that was step 3 to confirm that all the models in our ensemble have very similar IID evaluation performance. But now let's take a look at how each of these models in this ensemble perform on different stress tests, right? And so what we're doing here is we're plotting how each member of the ensemble performs with respect to the average performance of all the models in this ensemble, right? What we see is that there's orders of magnitude more variation in performance on these stress tests than there is on the original test set. So what this means is that while using the standard sort of machine learning pipeline of evaluating models based on their IID performance, we would think that these models are more or less identical, right? But then as soon as we start looking at how these models perform on different shifted data that correspond to realistic-ish, right, corruptions that we might see if we were to apply this model in the real world, right, we see that there is a a wide range of variability in terms of whether these models would actually be effective in any one of these situations. And so here we've highlighted in black just the performance of one of these models on all of these different stress tests. But you can see by the way that all these lines are crossing, right? Each of these lines corresponds to a single random initialization. Right, there is very little predictability in terms of for a particularly randomly initialized model, whether it's going to be very good on one of these on one of these stress tests based on its performance on any other stress test. And so this is behavior that we're able to replicate in the other sort of applied settings as well. So for example, in the retinal imaging case, right, the stress test that we chose was evaluating evaluating an ensemble of 10 models that again only differed in random initialization on a camera type that didn't appear in the training or test set. Right. And so when we looked at evaluating these models on a different camera type, we found that there was significantly more variation in the performance on that held out camera type. And while the additional variation here doesn't pop as much as it does with the ImageNet example, what you can see is that if you look at models whose, say, calibration characteristics look very similar on all of the camera types that appear inside the standard test set, we can see actually very different calibration behavior once we look at applying them on a held out test set, right? So there are a number of different properties of these models that are just not made salient if we only evaluate them on the standard test set that comes from a random train test split, right? And then similarly in the dermatology application that we considered, right? Here, if we think about stratifying the test set by skin type, what we see is that there is actually substantially different performance between different random seeds on different Fitzpatrick skin types, which correspond to different ways that certain conditions will manifest on the skin, and is also very strongly correlated with skin color. So, for example, here we see is that the IID performance of each one of these models is very similar to the performance on the most common skin type in the test set, right, which is of type 3. You can see an example here. But when we look at, say, skin of type 4, which is quite a bit rarer in the standard test set, we see that there's much more variability here. And even if you account for the fact that these sample sizes are very different, we still see that this is more variability than we would expect in terms of performance on say, skin type 4, even just from sort of random sampling alone. Great. Okay, so those were the vision examples. Now that I've sort of talked about this in a concrete way, I'm wondering if there are any additional questions there.
A question for myself.
Yeah.
Would ensembling multiple different models that perform similarly help this in any way, or
That's a really great question, and it's one that we looked at a little bit in this work, because for the most part, right, the way that we constructed these ensembles is actually right, the way that a lot of folks will construct ensembles for the purpose of averaging them together in order to get a model in the end. In fact, what we did was we went to a bunch of teams that were already doing this ensembling, and we asked them if we could just actually sort of take apart their ensemble models just to understand what the variability looks like. And so what we found was that when there's very large variability in the ensemble average will actually not outperform the best performing model in that. So for example, when we look at the pixelate task, right, the model that generalizes the best in terms of, here, let's go back. Right, if we look at this pixelate task here, right, the single model that generalizes the best on the pixelated data set actually does far better than the average of all of these models together. In other cases where there's less variability, we'll find that the ensemble average, if we average together, say, a subset of 10 of these models, will finally surpass the best model in the ensemble. But generally, right, we shouldn't expect, right, this is really a question about how each of these models is going to extrapolate to a new situation that wasn't necessarily, present in training. And so we shouldn't necessarily expect that averaging together a bunch of different hypotheses about that extrapolation is necessarily going to lead to something better, right? Because some of these sort of guesses at how the model, how the data is going to behave outside of the training domain are just plain wrong, right? If they're sort of extrapolating on the basis of a bad assumption, then averaging together a bunch of bad assumptions is not necessarily going to get you to a better place. And so I think this is a very interesting question that's also arising sort of in the Bayesian deep learning world right now. For example, there's a recent paper about using full badge Hamiltonian Monte Carlo to construct like true Bayesian posteriors of deep neural networks. What they found in that paper was that once you get this true Bayesian posterior, its out of domain performance was actually quite bad, right? Because we were just averaging together a bunch of these different hypotheses about how the model is going to perform out of the distribution. Again, a lot of those hypotheses are wrong. So what, in my mind, what this highlights is that if we want models to perform well out of distribution, right, there's something that we have to bring to the table beyond just what we can learn from the training domain itself.
Yeah, it seems like there should be some intelligent transfer from the different domains somehow back to the original domain. Yeah.
Yeah, exactly. Great. Okay. Any other questions about that?
We have 2 questions. We could do them now, or
I think that's fine. So, basically this talk is structured with like a laundry list of examples, so I can just skip the last example and answer questions because I think it'll probably be more relevant for the audience.
Okay. So I'm going to call on a few people to ask their questions. Michael, if you're around, can you unmute and ask your question? Oh, I think I only just allowed you to talk, Michael. So, yeah, let's see if you are able to ask your question now. I'm also gonna unmute Leaf as well. Yeah. Hi, Michael. Can you hear us?
Yes. Sorry, I'm like in the middle of brushing my teeth actually. But my question was on the sort of like. Oh, sorry. Can you just give me a second?
Yeah.
Oh, sure. Yeah, I will call on Leaf to ask his question first. Leaf, do you want to ask your question?
Yeah, I was wondering if there were any difficulties in identifying all the arbitrary choices that you wanted to, create an ensemble. Like it seems like there might be some that are not obvious.
Yeah, absolutely. So what I'll say is that for this paper, we really just focused on random seeds, but there are a number of other arbitrary choices that come up all the time, right? And actually, so I think, one way to think about this work, as I mentioned before, is that you can think about it as sort of running in parallel to work on constructing more diverse ensembles of models, right? Where those diverse ensembles are designed to sort of have very similar IID performance among all of the ensemble members. So for example, some of my colleagues have been working on what they call hyperparameter ensembles, where they look at a number of different hyperparameter choices that are being made when optimizing or tuning a machine learning pipeline. And when they find that many different combinations of hyperparameters give very similar IID performance, they look at ensembling those things together. And so I think those kinds of choices would make very good candidates for doing more extensive underspecification studies in the type that we did here. Really, we think about what we did in this paper as sort of a lower bound on like the variability that we pulled out. We think of that as sort of a lower bound on the region of underspecification, right? Sort of the like how much freedom is left over in these trustworthiness dimensions, even after we sort of enforce that the model meet the same IID evaluation criteria.
Cool. We have a next question from Benjamin. Benjamin, do you want to ask your question?
Yeah. I was just wondering if underspecification applies kind of the same way in self-supervised or generally unsupervised learning where you're not necessarily fitting to the noise of the supervised signal?
Yeah, absolutely. That's a really great question. And so actually one thing, I wonder if I have some of this here, right? Because we did do some experiments looking at pre-training. Oh, okay. Right, where you can think about, say, a BERT model as being right, a sort of self-supervised masked language model. Right. What we found was that even if you look at just these pre-trained models and you sort of probe the pre-trained model itself, you will also get very different performance on different stress tests that you might have. So, for example, there is an evaluation called StereoSet that's used to probe language models for different kinds of stereotypes. What we found was that if we, pre-trained 5 different BERT models from different random seeds using sort of the same training specification that appears in, the publicly released BERT models, we saw that the variability in terms of the StereoSet scores that came from those 5 different, self-supervised models was about as equivalent to like the top, I think it was the top 6 different architectures that appear in the StereoSet leaderboard on that website, right? So yeah, we see that there's also very, very strong underspecification in self-supervised models as well.
Oh,
Great, thank you.
I think Michael still wanted to ask his question.
yeah.
Oh, yeah,
And
sorry
Michael
about
next.
that. Yes. Thanks. Yeah. So I'm just curious. Maybe I interpreted the variability plots incorrectly, but ordinarily I'd expect that sort of all the models would perform less well in the like out of distribution evaluation distributions.
Yeah.
But it seems like some of them actually have some lift, and so I'm curious, like, if you have any like thoughts on this, or like how does this sort of like?
So this is.
affect
No, you're absolutely right that we presented this in a way to highlight variability and not the actual mean, right? So when we say relative accuracy here, what we mean is that we constructed z-scores with respect to the mean of the ensemble, right? And so what you would actually like, we have tables in the paper that actually show sort of how these ResNet 50 models perform on each of these on each of these stress tests. And you do see that there's very significant degradation of performance across all these stress tests for ResNet 50 models. Right. So the thing that we're focused on here is just the variability in the ensemble across all of these. But if we actually plotted this, you would see that like IID test performance would be high, and then like the performance on each of these would be low. Thanks. That's a great question.
Hi. I had a sort of a philosophical question.
Mhm.
Bear with me with this. So one way to interpret these results would be that the models have higher variance on out of distribution data than within distribution, right?
Yes.
And in a way, humans are also very similar, right? If I were to, for example, identify ethnicity of people within Southeast Asian, I'm much better at doing that than kind of regions where I have not really seen. So the models do have this human-like performance in that regard, and it's reasonable. So yeah, if you could just share your thoughts on that.
Yeah, absolutely. So I mean, I think this sort of human-like analogy is perhaps very apt, right? In the sense that, right, I think as humans, we sort of understand that there are going to be limitations to our ability to make decisions on like in different circumstances where that are sort of outside of the experience that we've had before, right? And in fact, like the way that we end up making decisions outside of that experience ends up sort of falling back on different like biases that we might have about how we're going to extrapolate to that new situation, right? So some people might assume, right, that this particular variable is the most important thing for trying to extrapolate to a new scenario, whereas somebody else might think that a different variable is the most important thing. And I think, right, when we are trying to make models trustworthy, what we're trying to do is to right, make sure that the model is making its decision on a basis that we think at least somebody would think is sort of reasonable. Right. And often, right, what we'd like to do is to have is to be very intentional about the way that we want models to be making decisions on new data. Right. So that it's not just sort of at the whim of a single person, but maybe something that's the result of actually thinking about, what kind of decision process on new data would actually lead to better outcomes out in the world. In fact, I think this is sort of a really nice way to segue into just some closing thoughts that I had about this and sort of what we should do about underspecification. Right, and so the way that I've been framing this, I actually really like the context around this Donald Knuth quote that I started out with, saying that machines do no more and no less than what you ask them to do. This actually comes from a bulleted list of sort of requirements that that Knuth has for any reader of the book. Right, and one of the requirements he has is an ability to put solutions to problems into such explicit terms that a computer can understand them. Right, this is sort of a minimal requirement for being able to write out the solution to a problem in as a program. Right, and so the way that I've been thinking about underspecification, right, is that what we need is an ability to put the requirements for problems into such explicit terms that a machine learning pipeline can understand them. Right. So what I mean by that, right, is that often we'll have a machine learning pipeline and we'll have a bunch of implicit requirements in our heads that we actually haven't put down into the particular training pipeline. And so when we posted this paper on Twitter, there was actually a really nice story that came out from this gentleman, Sergey Feldman, who talked about his experience training a machine learning model on an information retrieval task, right? And what they found was that often it was the case that if you added some features that improved their held out metric for performance, this would destroy some notion of qualitative performance. And likewise, right, they would find many models that had very similar sort of ranking performance, right? This NDCG ranking metric was very similar, actually behaved in very different ways when they were deployed. And so to try to determine what the correct behavior of such a system was, right, beyond just this single ranking metric, they actually had to sort of put together this very bespoke, hand-constructed set of things that looked like unit tests, right, just to make sure that the model was actually doing something sensible out in the world, right? And so I think that a number of people have probably had very similar experiences to this. Right, and what it means is like this entire sort of post hoc process that went on here is really sort of trying to make up for the fact that the way that we specify machine learning models right now is very incomplete, right? Because the predictive performance that we're usually optimizing for is necessary but not sufficient for a lot of the expectations that we have of the model. But these additional expectations that we have, right, that we sort of talk about as trustworthiness criteria, are actually very difficult to automate because they're usually functions of the context in which we expect to deploy the model, right? And so what this means is that in order to sort of satisfy these requirements, we really require processes outside of the algorithm. And the process by which we arrive at these requirements is going to be a fundamentally human process, and thus, it really does matter who's at the table when deciding on these requirements. So the way that I've been thinking about, moving forward from this work after thinking about underspecification for a while, right? We've sort of landed on a few different points where it seems like work is really necessary, right? So one of them is the specification point, or actually stating in a very systematic way what properties we require of a model in practice. I think this is probably the hardest part, and it's the most human part, right? After we arrive at something like a specification, then I think we can sort of iterate between that and testing or monitoring strategies, right? Or how we verify that these requirements are actually met. And then, right, I think after we've arrived at a nice way to try to translate these very human concerns into something more qualitative, or into something more quantitative, there are then questions about how we actually enforce these requirements during training, right? And I think that a lot of the machine learning world has focused on this last point here. And I think that's fine, because I think, right, we're only going to get conversations about how to test and enforce different requirements of machine learning models if we also have some notion of what the solutions are going to look like. But I think that all of these are extremely important. One thing that I want to highlight is that some of the most important work in this area has come not from trying to push forward algorithmic techniques, but to actually try to more formalize the process around designing an entire machine learning pipeline. Right. So if you think about data sheets for data sets, model cards for model reporting, right, there was a really nice paper from FACT a couple of years ago called Closing the AI Accountability Gap. Right. I think that these are some really important places to focus on when we sort of think about the holistic requirements that we have in the machine learning system. All right. So that's all the content that I had to talk about today. So we could do some more questions if there are some.
Yeah,
Sorry.
thanks, Alex, for the talk. If anyone in the audience, if you still have any technical questions, please ask them in the chat. I think there is one right now. Oh, Leaf again. Leaf, do you want to ask a question?
Yeah, I was wondering if you wondered whether any of these lessons can apply to a debate around reproducibility and what that means.
Yes, absolutely. So in fact, we have an ongoing project right now with a group of folks who work on natural language processing about producing some reproducibility guidelines. Because I think this is a really important question. And a lot of the things that we end up talking about when we're talking about reproducibility sort of go back to very fundamental question of, what is the thing that we are evaluating, right? Are we evaluating a sort of single output of a machine learning pipeline? Are we evaluating the machine learning pipeline itself and its ability to, to consistently produce good solutions to this type of problem? Right, and so I think there are, you will end up with different answers to those questions in different contexts, right? I think in the end, right, we care about reproducibility because, well, we often care about reproducibility because we want to focus on the method itself and not the particular decision function that came out of a particular run of a machine learning pipeline. Right, and when that's the case, when we actually care about the whole machine learning pipeline itself, that's really where it's important to focus on how to constrain that pipeline to return functions that not only satisfy our IID prediction criteria, but also sort of satisfy additional criteria that appear to be orthogonal. Yeah, but I think it is very it's very important here to sort of highlight that if we're going to say evaluate a set of models on a bunch of on a bunch of different dimensions, right, we need to make sure that we're actually measuring each one of those dimensions, and to the extent that it's necessary to say that we can very reliably make sure that a model sort of satisfies this criterion on this dimension.
Okay, I have one technical question, and then we'll do one of the journey questions. So we talked about like some model design decisions that like a random seed that really you should expect it to be the same, but really it's not. What about things like problems with data where, say, you have two very correlated features and you stick it in a model? Say even something as simple as linear regression. One of them might get picked up and the other one doesn't. So say you regularize it somehow, and it picks up one of them and not the other one, and so you have like a unique model now. Is that like according to your definition of underspecified, this is then not underspecified? But is that a good thing to not know that like the other one was correlated and could have been picked up?
Yeah, this is a great question. So we have an example of this kind of model in the paper as well, as sort of part of the warm-up. Before we talk about neural networks, there's an example in the paper about constructing polygenic risk scores from very highly correlated genetic variants, where you have a measurement of a patient's genome, you want to predict something that's clinically relevant based on that genetic information. So it just happens because of the way that different variations in the genetic code are sort of locally like physically very close to each other, that when crossover happens, you will often have like highly correlated variations in somebody's DNA. And so, you know, the standard thing to do for polygenic risk scores is linear models, right? And so you end up exactly with this kind of collinearity issue, where, yeah, very, very small changes to your learning pipeline can completely change, you know, what ends up in the model, right? And so this actually, I think, relates very closely to the sort of the maybe tangent that I went on for the misspecification question, right? Which is that, you know, if you are applying something like a form of regularization to a linear regression problem, it really depends on whether you think that regularization that you're applying is a design decision, or if you're thinking about it more like a hyperparameter, right? Like, is it something that you are sort of bringing some knowledge to the table and deliberately designing to say, okay, I really do think that L2 regularization is the right thing to do in this context? Or are you just saying, well, maybe L2, maybe L1, maybe some other kind of like sparsity regularization or something is a better thing to do here. I really don't care. All I want is better IID predictive performance, right? And in that case, if you're sort of agnostic to the kind of regularization, you could think about sort of expanding your problem a little bit to say, I don't just care about ridge regression here. I care about any kind of regularized linear regression. And right, in that case, right, within the sort of ridge regularized class, you're probably going to have a best model. In the L1 regularized class, you're probably going to have a best model, right? In the elastic net class, you'll probably have a best model, right? And those models may end up having very similar sort of IID performance, right? So if you thought about the sort of expanded set of problems, you would end up again in an underspecified problem. But I think, you know, the more important thing to highlight there is that this regularization decision that you're making is actually it has very real world consequences, right? And right, it's going to make a big difference when you try to take that model to a domain where those variables are no longer as correlated as much, right? The regularization decision that you made is going to really determine how that model is going to extrapolate to that new setting. Yeah, and so if you end up making that decision, you know, arbitrarily, or you know, or it's part of sort of an outer loop of model specifications, right? The key idea here is that a decision that you made for convenience ends up affecting the trustworthiness of your model.
I feel like this is such a meta decision.
Yeah.
Yeah.
Yeah. It's
Okay. Let's do a journey question.
Sure.
We have a lot of students who come to our seminars. So can you talk a bit about your journey? You know, what motivated you to do what you do today?
Yeah.
Your current position. You know, you were, I guess, an Neyman Assistant Professor at Berkeley, and then, you know, change from academia to industry. So yeah, a little bit about your journey. Yeah, absolutely. So, you know, I did my PhD in statistics. If you talk to me while I was a grad student in statistics, I would roll my eyes every time somebody said machine learning. Like, I was a very sort of dogmatic, parametric, Bayesian type person, I guess. And then but I always sort of had this very strong interest in understanding what kind of statements are like truly justified by the data that we're using to try to solve a problem. And that set of questions led me to start thinking more about causal inference. So when I moved from my PhD to doing a visiting assistant professorship afterwards, the visiting assistant professorship, for those who don't know, is basically like a fancy postdoc, right? It's a fixed term appointment where you teach some classes, you get to call yourself a professor, but for all intents and purposes, it's sort of a postdoc appointment. So during that postdoc, I reconnected with you know, some of my former cohort mates who had been working very seriously on causal inference for a while, and ended up pivoting my research direction there, which is like generally a very hard thing to do. And the only reason I was able to do it was because I had very strong support from, you know, a set of people who could connect me to that new community.
and so upon getting connected to the causal inference community, I started thinking a lot more about questions of identification, right? And sort of if we think about the observed data as constraining the model that we're using in this way, right? What are the set of conclusions that are still compatible with the set of constraints that the observed data has given us? So I've worked a lot on causal problems that way, and then so to be like totally honest, the way that I ended up in industry was that I wanted to continue being an academic, but I had a very strong geographic constraint, and decided that it was more important to be in Boston, in a place where my family preferred to be, and at that point, I had very limited academic options, but I had an opportunity to sort of jump over into machine learning research in industry. And I'd say that opportunity worked out much better than I anticipated it would have at the beginning. And one piece of advice that I would give would be for, even if as a student you have a very strong, preference for one particular career path, whether that's industry or academia, it is really worthwhile to make sure you've sort of vetted the other possible career paths as well. This was certainly a career path that I had not anticipated I would end up in. But sort of retrospectively, I think this ended up being a much better fit for me than sort of standard assistant professor life would have been. So.
Cool. Thanks so much, Alex, for the advice and the talk as well.